find the endpoints of that confidence interval is we have to have a known X bar. We have to have a sample that we've measured the mean. We need to know that sigma for now. And when we switch to the t distribution, we'll be able to switch to our known standard deviation. This is a sample, so it has a sample size. And then we need this Z star. Right, so the Z star is a value that we are going to know based on what we set for our confidence interval. Right, so the Z star, we're going to find using C, right? We're C% confident. We're going to have our standard normal curve here. That C area is going to be in the middle here, right? And then we're going to find these Z values based on that particular C. Right? And those are going to be the Z star. So we first have to set our C, and then we'll find the values of Z star. And then we can calculate the endpoints of our confidence interval using these very simple equations. So we're just going to take X bar, and then we're either going to add or subtract this quantity Z star times sigma over root n. Right, so this is pretty easy math-wise. Interpreting what it means may be a little harder. And we're going to find these values of Z star using the standard normal distribution. Now, there's ones we use often, right? And remember that when we are finding those Z stars, our standard normal table, is going to give us an area to the left, right? But what we want when we're looking for our Z star values is we want that area not to be to the left, but we want it to be in the middle. Right. So if you go to the standard normal table and you find a Z star value of 1.645, you're not going to see that 0.9 of the area is to the left of it. Right. We'll look at how to do that in just a minute. So you should come back and you should practice finding these for the 90%, 95, and 99%, these values of Z star. We use these all the time. I've memorized 1.96 because you just use it all the time. All right, so for any area C under the curve, we find the Z stars for it, and then we're going to calculate this quantity, this Z star times sigma over root n, and it is called the margin of error. Sometimes you hear that being discussed when they're reporting in the news the results of a survey or a poll. You know, the candidates are within whatever margin of error of one another, 1% margin of error. So that bigger the margin of error, the bigger the uncertainty is about what the actual value is. And there's a lot of different contexts that we might want to use this information. All right, so how do we find those Z values? Let's look at this in a little bit more detail. So we're going to have this area C that's going to be in the middle of our distribution. So we're going to have the leftover distribution, 1 minus C, right? If this area C is in the middle, a total of 1 minus C is left over in the tails in the green area. Half of it's on one side, half of it's on the other because our distribution is symmetrical. And so we're going to find the values of Z by first finding this 1 minus C over 2. That tells us this area that's in our left-hand tail. Right, and then we can go to the standard normal table and find the negative Z value that's associated with it. Our positive, our negative Z values are going to be the same. All right, so there's a couple properties of confidence intervals that we need to understand. One is that the higher our probability is, the more, the bigger the C, right? That makes the Z stars go further apart, okay? So those values of Z star are going to be bigger. that makes our confidence interval wider, right? So when we look at how big a confidence interval is going to be, if we have a 90% confidence versus a 95% confidence versus a 99% confidence, because those Z stars are further out, we have more of the distribution in the middle, the confidence interval is going to get wider, right? Can we do 100% confidence interval? No, we can't, because that normal distribution keeps going on forever, right? We'd have to have a very, very, very wide distribution. And once it's that wide, like if you think about all the values of X that our value could be across the X-axis, the wider our confidence interval gets, the less well we know what the true mean actually is. So there's a trade-off between how sure we want to be that we have caught the true mean versus what we know that the value actually is, right? So if we choose to have a 99% confidence, sure, we're really confident, we're 99% confident that our sampling, our confidence interval is catching the true mean, but we don't know what the true mean's value is. It's somewhere between 21 and 31 micrometers per hour, right? So we're really sure we caught it, but it could be anywhere, 10 units across our X-axis here. Right, so if we have our 90% confidence interval, we're less confident we're catching the true mean, we have a better idea what the true mean actually is, right? So if we narrow down for the 90% confidence, we know that it's somewhere between 22.5 and 29.5, right? So we're more sure what the value is, but we're less sure we have it, right? So what we want to do is find a confidence interval. Right, so how this might be written is find a 95% confidence interval for a sample of wood lice, also known as roly-polies, with a mean of 0.79 centimeters. Suppose we know sigma, it's 0.14 centimeters, and our sample was 75 individuals, right? So for a 95% confidence interval, C equals 0.95. And we talked about the fact that Z star equals, 1.96. Right, so for 95% confidence interval, we know this already. So all we're going to do in order to find the confidence interval is we're really finding the endpoints of the confidence interval, which is going to be written X bar minus this margin of error and X bar plus this margin of error. And this is sort of interval math notation. So we are finding these endpoints of the confidence interval. The margin of error is going to equal Z star times sigma over root n. And for this example, the math is really easy. We're going to take 1.96 times sigma over root 75, and we're going to do X bar plus or minus that. And the reason I have a plus and a minus here is that I'm going to add it to the mean, and I'm also going to subtract it from the mean. So this is two different mathematical operations. So I'm going to find X bar plus or minus. When I calculate the margin of error, I get 0.03. So the endpoints of my confidence interval are going to be the mean 0.79 minus 0.03, which equals 0.76, 0.79 plus 0.03, which equals, I'm going to time it up today, 0.82, and I'm going to write my finished answer. All right, what does this tell me? This tells me that my roly-polies on average were 0.79 centimeters, and that if I went and I did this exact same new sample over and over again, 95% of the samples that I took, that the true mean would be between 0.76 and 0.82. And so I'm pretty confident that the true mean size of my roly-polies is in this interval. Right. Now, suppose we didn't want to do an 85% confidence interval. We wanted to do some other one that was more goofy. So suppose we had a 75% confidence interval. All right, so what we want to do, everything else is going to be the same. We're going to have a different Z star. Right. So our C equals 0.75. We need to find the values of Z such that 0.75 is in the middle. That means we're going to take 1 minus C over 2. That's in this tail here. Right? It's also in this tail over here. So we can do 1 minus 0.75 over 2. And that gives us 0.125. Right, now we're going to go to the standard normal distribution. We're going to go to the standard normal distribution, and you're going to look on the minus side. Standard normal distribution. Right, and you're going to find this value 0.125 in the table, and you're going to, or as close as you can, and you're going to go to the left and to the top, and you're going to find the value of little z that makes the value in the table be 0.125, right? And that is 1.15, right? Remember, this part of the number is on the left-hand column, and this part, the far left-hand column, and this one is in the row at the top, okay? So make sure that you have found this value in the standard normal table. Now, all we're going to do to find the endpoints of our interval is we're going to do x bar plus or minus 1.15 times 0.14 over the square root of 75. All right, so we just substituted this different z star in there, and we should get, right, a 75% confidence interval is going to be skinnier, right? Our z star was 1.96. Our z star for our 75% confidence interval is 1.15. And so when we make this calculation, we find that, what does this come out to be? Didn't actually calculate it on my example. All right, so whatever this value is, you're going to do x bar minus the margin of error, x bar plus the margin of error. All right, so it should be skinnier. So we're less sure that the true mean is in there, but we're more sure that the value is. The calculation of what we do to find the confidence interval is very easy. The hard part is finding those z stars if it's not one that we used already. All right, so the next kind of inference that we're going to do is to assess a claim about the population. And we're going to do this by doing what is called a hypothesis test, or a test of significance. And we're going to use a special kind of logic in order to make this work. So we're always going to have a hypothesis about a parameter, not about a statistic. A statistic we know, right? The parameter we don't know. So we're going to put for example, we're going to put mu into our hypothesis, then we're going to calculate X bar and use it as an estimate, right? And we're going to compare the data that we collected to what we put in the hypothesis. But we have to have two hypotheses. And the reason for that is that we want to have a complete sample space. We want to have the probabilities or the things that can happen for the complete sample space S. The only two things that can happen are H sub 0, the null hypothesis, and H sub A, the alternate hypothesis, right? Because according to the Popperian falsificationist paradigm, which we operate under, we can't prove that a hypothesis is true, but we can disprove a hypothesis. So we're going to use this sneaky kind of logic and say, okay, we're going to try and disprove our null hypothesis. And if we disprove it, and it's the complement to the alternate hypothesis, then we have supported the alternate hypothesis. And notice we still aren't saying we proved the alternate hypothesis, but that's the logic of how we're going to go about doing this. So we're always going to have our null and our alternate hypothesis. The null hypothesis is always going to be nothing happened. This value is equal to one specific value and no other value. So we're actually making the null hypothesis actually a very teeny part of the sampling space, and then sort of anything happened is the rest of the sample space. All right. So what we're going to do is use for estimating a mean, we're going to use the central limit theorem. We're going to use the sampling distribution because we're going to have a sample. We're going to say, okay, suppose my mean is something in particular, right? So we're going to have our hypothesis about this parameter. So our null hypothesis is going to be that mu, the true population parameter, equals something. And in this example, our hypothesis is that our null hypothesis is that it equals 0, right? We're going to take a sample and we're going to have a standard deviation in the sample size so we can calculate this value, the standard deviation of the sampling distribution. And we're going to look at our X bar, right? So based on this normal distribution that is set up by our null hypothesized value and our sampling distribution standard deviation, for any value of X that I get, X bar that I get, I can evaluate what's the probability that this X bar is as far away from the true mean, if it's really true, as the one that I got. Right. So we want to look at these probabilities for these two different examples of what we could get as a value for our X bar. So suppose we got a value of our X bar that equals 0.3. Right. We're going to say, what's the probability, assuming that null hypothesis is true, assuming the true mean is really 0, what's the probability that I get a value of my X bar this far away from my hypothesized value, right? That probability is pretty big. I don't know, it's like a quarter, it's like a third. Probability that that I would get a value this far away from my true mean, assuming my true mean is true, is pretty big. It's pretty likely, right? Now contrast that to the scenario where if my X value comes out to be 1.02, right, way over here, the probability that if my mu 0 really is 0 over here, the probability that I get a value this far away from it or farther is going to be this little tiny area over here. All right, so a very small probability. I'm going to use that probability to say, how likely is it that my hypothesized value really is the true value? Okay, so based on the evidence, based on my sample, I have proposed this null hypothesis. If my sample mean is close to it, I'll say, it's pretty likely that that proposed mean, that hypothesized mean, is actually the real mean, right? But if I get a value of X bar that's way over here, the probability that that would happen, if this were really true, if this null hypothesis were really true, is pretty small, right? So either I just got this really unusual sample, or this is not a good hypothesis, right? So in this case, we would want to say that our null hypothesis isn't very likely, right? So way over here, we're going to reject the null. And over here, we're going to accept the null. All right, so that's basically the way that our hypothesis testing is going to work. We're going to set up our hypothesis. We are going to use these values of X bar compared to our null hypothesis value to find these areas under the curve. But we do need a cutoff value to let us know like exactly where. Like it's obvious that this one is quite far and this one over here is not very far, right? So it turns out we're going to arbitrarily set a value that we're going to use as a cutoff for how far is far enough away in order to reject the null. Right, so when we have any data, right, we have any data and we have any hypothesized value, and we want to convert it to the standard normal distribution so that we can find these probabilities using the normal distribution, right? So we're going to still use, so we have this mu in our hypothesis, and then we have this X bar. Right, so in order to convert our data into the standard normal distribution, we're going to use the same formula that we've been using all semester, z equals. Now we're going to have X bar minus mu 0 in that equation. But we're still going to have sigma over root n, just like we did for sampling distribution. Right, so this mu sub 0, we get it from our null hypothesis. And the X bar has to be given in the data. All right, so we have this null hypothesis, and it's always going to be for this very, very simple kind of test we're doing today, which is called a z-test. A z-test is going to be a test to see if the mu of our distribution equals a specific value. All right, so if we're going to sub a specific value in there, we're going to call it mu sub 0. All right, now if that's not true, then one of three things could be true. It could be true that the mu is actually greater than 23. It could be true that mu is less than 23. And it could be true that all we care about is that mu does not equal 23. So if mu does not equal 23, we're actually sort of combining these other two potential hypotheses together. We're saying, well, we want to find out if mu is less than 23 or it's greater than 23. So we are going to define these two types of hypotheses where we're only looking at greater than or less than. We're going to call these one-tailed hypotheses, and we're going to call this one two-tailed, right? Because it includes both the tails of the distribution, and the other ones only include one tail of the distribution. So when we're finding our probability using our standard normal distribution, if we have a one-tailed alternate hypothesis, then we just find the value on the standard normal distribution and we're done, right? If we have a two-tailed hypothesis, we're going to find that probability and then we're going to multiply it times 2. Right, because we want to include both ends of the distribution. Right. How do we know we're doing a one-tailed or a two-tailed hypothesis? It depends on the research question that we're asking, right? So when you are reading a problem and it says we want to find out if there is a difference in roly-poly size between these two sites, then we're asking a question using a two-tailed hypothesis. We want to know, is it different? We don't care whether it's larger or smaller. We just want to know if it's different. if the question says we want to know if the roly-polies at this site are smaller than the ones at this other site, all right, then we have an alternate hypothesis that is this H sub 2, right? Or if we want to ask a question, we think these roly-polies are larger at this site than this other one because they have whatever better resources, we could be asking the question, is the mu greater than this value of 23 in particular? Right, so the way you decide whether you should be doing a one-tailed or a two-tailed hypothesis test is in how the question is written. All right, so what we're doing when we do these hypothesis tests is we're saying, okay, I'm going to set up a scenario where I'm going to assume the population really has this parameter. What's the probability, capital P or little p sometimes, of observing a value as different from mu as the statistic X bar that I did observe? All right, so that probability is that area under the curve further away from mu sub 0 than your X bar. If that probability is small, either we observe something unusual or our estimate of that parameter is not good. If the little p is large, then our estimate of the parameter is good. There's a high probability that we would get a sample with mean X bar if the true mean was actually mu 0. Right, so this is the definition of our p-value. Our p-value is the result of our statistical test mathematically. It is the probability of getting an outcome as extreme or more extreme than the observed outcome due to chance alone, assuming the null hypothesis is true. So basically, this diagram, right, I've got my mu sub 0 in the middle there. I'm assuming my H sub 0 is true. That's this part, right? What's the probability of getting an outcome as extreme or more extreme than the observed outcome, right? That's what I'm doing when I put my X bar on here and I find the probability that's further away, right? That's an outcome as extreme or more extreme than the observed outcome, right? Due to chance alone means there's nothing going on here. If I really took a random sample, my experiment is well controlled, there is no effect, right? There's nothing going on in the experiment except the thing that I'm focused on, right? So this due to chance alone is important. So there's 4 component parts to this definition of the p-value. The idea that it's a probability, right? So this area under the curve is our p-value if we're doing a one-tailed test. All right, probability, getting an outcome as extreme or more extreme than the observed outcome due to chance alone, assuming the null hypothesis is true. And we're always going to put the null hypothesis in the middle of our normal distribution. Right, how small does our p-value have to be in order for us to decide it's far enough away? Well, we're going to set this value alpha in advance, and often we're going to set alpha to 0.05, right? We can also have an alpha equals 0.01. We're usually going to use one or the other of those values for alpha. The p-value is less than or equal to alpha. We're going to say that the difference is statistically significant. So if you've been waiting to use this word significant, now is the time, right? So did we find a statistically significant difference between our hypothesized value and our sampled value? That's what we're going to be able to say. All right, now we have to set it in advance, and that's important so that we're objective. We don't want to get our p-value and then say, oh, it's not that small. Let's see, it's 0.03. I'm going to use an alpha of 0.05, and therefore I'll be able to reject my null, right? You don't want to do that. You want to set it ahead of time. All right, so why don't we just set a really small alpha? Well, it turns out that like everything in life, there's trade-offs. All right, so notice that we have alpha here. So what we're doing when we set alpha is kind of the opposite of what we're doing when we set a capital C for a confidence interval. Confidence interval is what the probability we want of catching the true mean. Alpha is actually the probability of making a mistake, and it's called a type 1 error. A type 1 error happens when the null hypothesis is actually true, but what we do is we reject it, right? So if we set that type 1 error to be very small, it turns out we actually are going to inflate the possibility of this other kind of error. There's two kinds of errors we can make. If the null hypothesis is true, but we reject it, that's a mistake. If the alternate hypothesis is true, and we don't reject the null, if we accept the null, then we have another kind of mistake or error that's called beta. All right. So we don't want to just make alpha really, really small, because we have this balance between making these two different kinds of errors. 1 minus beta is one kind of correct decision called power. And so often we talk about this balance between alpha and power. All right, so alpha and power. And there's ways to calculate power. There's ways to set power for your experiment. Having a large sample size really helps. But what I want you to know is what are, on this little grid, what are correct decisions, what are errors, which one is type 1, which one is type 2. So whether these kinds of errors are actually really important or not depends on the context. So let's talk about two examples. And in the health industry, typically we do all kinds of tests to see if we have certain diseases, if we have certain conditions, if we're pregnant, if we have COVID, all these types of tests. All right. So the null hypothesis for all those tests is going to be that we don't have the disease, right? That we don't have the disease. So if we take the test, if we don't have the disease, if H0 is really true, and we take a test and it tells us that we should reject the null hypothesis if we really don't have the disease, right? But the test tells us that we do, that is a false positive, right? We're really not sick, but we got a positive result on the test. If we make the other kind of mistake, we are actually sick, but the test tells us we don't have the disease, then that's a false negative, right? So depending on the consequences of these decisions, the makers of these kinds of tests will tune the amount of type 1 and type 2 errors, false positives and false negatives. So think about different kinds of tests and what the consequences would be if you didn't know or you did know. Like, would you want the same type 1 error for a pregnancy test as you would for an HIV test? What would be the different, or for a test for some kind of cancer, or a test for whether you have, you know, a common cold or COVID, right? What are the consequences of that? Another example is in our judicial system. So here in the United States, our null hypothesis is the person, the defendant, is innocent unless proven guilty, right? So the null hypothesis is that the person is innocent, right? So if the person really is innocent, but they're convicted, then that's a type 1 error, that's a wrongful conviction, right? If the alternate hypothesis is true, however, if the person really did the crime and they are not convicted, right, then that's a type 1 error. That is a person who is free even though they were guilty. All right, so that's how the system is supposed to work. It's supposed to be balanced so that we're more likely to make type 2 errors. Our legal system was intended to make more type 2 errors than it makes type 1 errors. Whether that actually works out in point of fact, and if it does that equally for all different kinds of people, especially different racial groups, we know that that's not true, but in every human human created system, there are going to be flaws, and hopefully that our country can get its act together and start doing a much better job at being fair to all different types of people who are coming into the criminal justice system. In the civil justice system, it works in a similar way as well. All right, so we also want to increase power. Power is a good thing. And the easiest way that we're going to be able to do it is to increase sample size. All right, so when we're looking at, we've done an experiment or we're designing an experiment, we want to try and design it so that it has good power, so that we can tell if there is a difference between our different groups. We have certain situations, though, where if we have a really, really big sample size, we're almost always going to come up with a significant result. So if it's something that we can measure it, we can compare it, but is it meaningful for the organism that we're studying? We have to keep that in mind too. So when we're doing and we're interpreting the results of statistical tests, we need to think about the context of the organism and all the things that you know about its biology, and think about whether the way you've done the experiment has come up with something that really matters, that makes a difference. The level of significance of a 0.05 was literally set, 100 years ago by this guy who said, hey, suppose we did a significance test and we set alpha at 0.05. And we've all been doing it that way ever since. Is there a reason why it's that particular number? Not really. 5% seems small. There are movements to do other kinds of statistical inference that don't use a set p-value. Types of inference that evaluate multiple competing hypotheses and find out which one is best supported by the data rather than setting a significance level. So as you go on into higher level of statistical class and context, different types of data, different types of science are done using sometimes these alternate forms of significance test or not significance testing, right? But this is a basic introductory way to think statistically, and it is the appropriate one for you to be learning at this level, right? So we don't just keep doing a bunch of different tests until we find something that's statistically significant. We want to design our experiment using the best information we have. And if it comes out significant, then that's great. If not, then we change our hypothesis. Maybe we need to do the experiment over again because something went wrong or it doesn't have very good power or whatever. But we don't want to just manipulate things in order to get a significant result. Does that make sense? Okay. So the steps that we're going to go through in order to do a significance test, and we're going to keep doing this for the whole rest of the semester, every different kind of test that we do. So we're going to march through a whole bunch of different kinds of tests. We're going to state a null and alternate hypothesis. We're going to calculate the value of a test statistic. And that test statistic is going to compare the observed sample to the hypothesized value. That's what it's going to do in every single different kind of test that we do. We're going to use some distribution, not always the normal distribution. We're going to use some distribution to find the p-value. And then we're going to compare the p-value to that pre-specified alpha level. P is less than or equal to alpha, we're going to reject the null, accept the alternate. P is greater than alpha, we don't reject the null. All right, so that's really important thing to keep in mind. If P is less than alpha, reject the null. All right, you have to remember that. All right, if P is less than alpha, like, wait, is P bigger or smaller than alpha? Wait, what do I do? All right, you need to remember that. All right, so we have gotten to the point where we are able to do a test of statistical significance. And I found this cartoon a while ago where this person is talking about their boyfriend. And she says, wait a sec, you spend twice as much time as me with anyone else. I'm a clear outlier. And so she says, I'm your statistically significant other. Now, she didn't really do a hypothesis test here, but she's using this phrase in a more or less correct way. And we're either going to say there is a statistically significant difference or there is not a statistically significant difference. This is not English class. It's going to sound awkward. And I am going to do an example to walk you through all of the steps. So let me unshare my screen. Web's examples besides this one. Okay, so I have roly-poly lengths. I measured them at building 30. And got an X bar of 0.79. Now, I also measured them, or a bunch of students measured them, I should say, at building 42, and they found an X bar of 0.9 centimeters, and a sigma, suppose we know it, of 0.26 centimeters, and a sample size of 46. All right, so this is my sample. And I've got a sample size over here. My sample I'm going to use to test my hypothesis. And in this case, I want to know, are my roly-polies from building 2, are they the same size as building 30? And so are roly-polies from building 42 the same size as RPs from building 30, right? So I'm curious if they're the same size. I don't care if they're bigger or smaller. So my null hypothesis is going to be that, right, and I'm going to use this notation, H sub A, H sub 0, I'm going to use a colon. My mu 0 equals, right, what am I asking? Are my 42 roly-polies the same as my building 30s? So my mu 0 is going to be 0.79. And then is my mu 0 not equal to 0.79? So this is a two-tailed alternate hypothesis. And we don't need to know that until we find the p-value or whether we multiply it by 2 or not. I'm going to set an alpha equals 0.05, because I want to set that ahead of time as well. All right, so I've written down my hypotheses. My next step is to calculate my test statistic. In this case, I'm doing a z-test, so my test statistic is z. Well, what does z equal? Z equals x bar minus mu 0 divided by sigma over rho n. I've got all these values up here. My mu 0 is in my hypothesis. We have our x bar is 0.9 minus our mu 0 divided by sigma 0.26 over rho n. And that equals 2.87. So what I want to do is find this probability. And actually, I want to find the equivalent value over here because I'm doing a two-tailed test and add those both together. All right, so what I've done is I've converted to the standard normal distribution with mu of 0. And what is this value equivalent to? 2.87 as a z. So my value of x, I've converted it to a value of z. Now what I want to do is go to the standard normal distribution. And I want to find the area to the right of this, but I also want to find the area to the left of negative 2.87. All right, so I'm going to find probability that little z is less than negative 2.87. Go to the standard interval tables. I'm going to find that's 0.0021. So my p-value is going to be 2 times that, because I have a two-tailed test. All right, now I'm going to ask the question, is my p less than my alpha? 0.0042 less than 0.05. Yes, my p is less than my alpha. What am I going to do in that case? I'm going to reject my null. Right, so I'm going to go up here and look at what my null was. I'm going to reject mu0 being equal to 0.79. I'm going to accept my alternate, right? And because I rejected the null, right, my p-value was small, I'm going to write out my result here. I get to say, I found that there was a statistically significant difference, right? So building 42 roly-polies have a statistically significant difference in size compared to building 30 roly-polies. All right, your statistically significant difference. All right, so this whole phrase, statistically significant. Now, if we had found our p-value was, 0.7 or some larger value, and we did not reject the null, right, we go through these same steps. Is p less than alpha? No. No. What do? I do not reject the null. All right, in that case, I accept the null, and I would say building 42 roly-polies do not have a statistically significant difference in size. Right, it's a little convoluted and awkward, but that is right in science when we're using these types of hypothesis tests. All right, so we will do this over and over and over again. Every hypothesis test we're doing the rest of the semester, we're going to write these very pedantic and boring sounding sentences, but we're being very clear about exactly what we found and using the language that all the other scientists are going to understand exactly what you mean.